Hi everyone, welcome back to this video series on the Comptia Security Plus course, Fuzz Testing. Fuzz Testing, also known as fuzzing or dynamic analysis, is another smart concept. This is where random data is inputted into a computer program in an attempt to find vulnerabilities. This is often done without knowledge of the source code of the program. The program to be tested is run, has data inputted to it, and is monitored for exceptions such as crashes. This can be done with applications and operating systems. It is commonly used to check file parsers within applications such as Microsoft Word and network parsers that are used by protocols such as DHCP. Fuzz testing can also uncover full system failures, memory leaks, error handling issues. Fuzz testing is usually automated, a program that checks a program, and can be as simple as sending a random set of bits to be inputted to the software. However, designing the inputs that cause the software to fail can be a tricky business, and often a myriad of variations of codes need to be tried to find vulnerabilities. Once the fuzz test is complete, the results are analysed, the code is reviewed and made stronger, and vulnerabilities that were found are removed. The stronger the fuzz test, the better the chances that the program will not be susceptible to exploits. As a final word on this, once code is properly tested and approved, it should be reused whenever possible. This helps to avoid recreating the wheel and avoids common mistakes that a programmer might make that others might have already fixed. Just remember, code reuse is only applicable if the code is up to date and approved for use. Programming vulnerabilities and attacks. Let's discuss some program code vulnerabilities and attacks that exploit them. This section gives specific ways to mitigate these risks during application development, hopefully preventing these threats and attacks from becoming realities. Backdoors. To begin, applications should be analysed for backdoors as mentioned in Chapter 2, Computer Systems Security Part 1. Backdoors are used in computer programs to bypass normal authentication and other security mechanisms in place. These can be avoided by updating the operating systems and applications and firmware on devices, essentially by carefully checking the code of the program. If the system is not updated, a malicious person could take all kinds of action via the backdoor. For example, a software developer who works for a company could install code through a backdoor that reactivates the user account after it was disabled for whatever reason, termination, end of consulting period, and so on. This is done through the use of a logic bomb in addition to the backdoor, and could be deadly once the software developer has access again. To reiterate, make sure that the OS is updated and considered a job rotation where programmers check each other's work. Memory buffer vulnerabilities. Memory and buffer vulnerabilities are common. There are several types of these, but perhaps most important is the buffer overflow. A buffer overflow is when a process stores data outside the memory that developer intended. This could cause erratic behavior in the application, especially if the memory already has other data in it. Stacks and heaps are data structures that are affected by buffer overflows. The stack is key data structure necessary for the exchange of data between procedures. The heap contains data items whose size can be altered during execution. Value types are stored in a stack, whereas reference types are stored in a heap. An ethical coder will try and keep these running efficiently. An unethical coder wanting to create a program vulnerability could, for example, omit input validation, which could allow a buffer overflow to affect heaps and stacks, which in turn could adversely affect the application or the operating system in question. Let's say a program allows for 16 bytes in a string value. This won't be a problem normally. However, if the program fails to verify that no more than 16 bytes could be copied over the variable, that would create a vulnerability that an attacker could exploit with a buffer overflow attack. The buffer overflow can also be initiated by certain inputs, for example, corrupting the stack with no operation, no op and nope machine instructions, which when used in large numbers can start a nope slide, can ultimately lead to the execution of unwanted arbitrary code or lead to a denial of service DOS on the affected computer. All this can be prevented by patching the system or application in question, making sure that the OS uses data execution prevention and utilizes bonds checking, which is a programming method of detecting whether a particular variable is within design bounds before it is allowed to be used. It can also be prevented by using correct code, checking code carefully and using the right programming language for the job in question, the right tool for the right job, yes, without getting too much into the programming side of things. Special values called canaries are used to protect against buffer overflows. On a semi-related note, integer overflows are when arithmetic operations attempt to create a numeric value that is too big for the available memory space. This creates a wrap and can cause resets and undefined behavior in the programming languages such as C and C++. The security ramification is that the integer overflow can violate the program's default behavior and possibly lead to a buffer overflow. This can be prevented or avoided by making overflows trigger an exception condition or by using a model for automatically eliminating integer overflow, such as the cert as if infidelity range AIR integer model. More can be learned about this model at the following link: www.cert.org/security coding tools/integer security.cfm. There are memory leaks. A memory leak is a type of resource leak caused when a program does not release memory properly. The lack of freed up memory can reduce the performance of a computer, especially in systems with shared memory or limited memory. A kernel level leak can lead to a serious system stability issues. The memory leak might happen on its own due to poor programming, or it could be that code resides in the application that is vulnerable and is later exploited by an attacker who sends specific packets to the system over the network. The type of error is more common in languages as C and C++ that have no automatic garbage collection, but it could happen in any programming language. There are several memory debuggers that can be used to check for leaks. However, it is recommended that garbage collection libraries be added to C, C++ or other programming language to check for potential memory leaks. Another potential memory related issue deals with pointer dereferencing. For example, the null pointer dereference. Pointer dereferencing is common in programming when you want to access data, say an integer in memory. Dereferencing the pointer would retrieve different data from a different section of memory, perhaps a different integer. Programs that contain a null pointer dereference generate memory fault errors, memory leaks. A null pointer dereference occurs when the program dereferences a pointer that it accepts to be valid but is null, which can cause the application to exit or the system to crash. From a programmatical standpoint, the main way to prevent this is malicious coding. Programmers can use special memory error analysis tools to enable error detection for a null pointer dereference. Once identified, the programmer can correct the code that may be causing errors, but this concept can be used to attack systems over the network by initiating IP address to hostname resolutions. Once the attacker hopes will fail, causing a return null. What all this means is that the network needs to be protected from attackers by attempting this programmable a memory-based attacks via network connection. A programmer may make use of addresses space layout randomization ASLR to help prevent the exploitation of memory corruption vulnerabilities. It randomly arranges the different address spaces used by a program or process. This can aid in protecting mobile devices or other systems from exploits caused by memory management problems. While there are exploits to ASLR such as side channel attacks that can bypass it and de-randomize how the address space is arranged, many systems employ some version of ASLR. Arbitrary code execution. Remote code execution. Arbitrary code execution is when an attacker obtains control of a target computer through some sort of vulnerability, thus gaining the power to execute commands on that remote computer at will. Programs that are designed to exploit software bugs or other vulnerabilities are often called arbitrary code execution exploits. These types of exploits inject shell code to allow the attacker to run arbitrary commands on the remote computer. This type of attack is also known as remote code execution (RCE) and can potentially allow the attacker to take full control of the remote computer and turn it into a zombie. RCE commands can be sent to the target computer using a URL of a browser or by using the netcat service. Among other methods to defend against this, applications should be updated, or if the application is being developed by your organization, it should be checked with Fuzz Testing and strong input validation client side, server side as part of the testing stage of the SDLC. If you have PHP running on a web server, it can be set to disable remote execution of configurations. A web server or other server can also be configured to block access from specific hosts. So I'm going to leave it here today for this video. If you like listening, please consider like, sharing and subscribing. Thank you.